a wonderful conference. So yeah, there's one person. There's one person. So my talk is about functoriality of our Khovanov homology. So there will be a little bit of overlap between my talk and Dean's talk from Wednesday, but I hope not very much. And everything that I'm going to talk about is joint work with Jacob Mcdale. So I'll start. Oh, maybe I'm doing this wrong. That's not funny. Let's see. Okay, so I'll start. Let's see how this works. Can I do this better? Okay, so let's change the slideshow. Okay, so I guess we all know even Khovanov homology. So to a link diagram, it assigns some bigraded homology group, and to any smooth link cobordism, it assigns a linear map. And this map is known to be invariant under smooth ambient isotropies of F, so it gives you an invariant of the link cobordism. And this invariance property was first shown by Jacobson, and later Khovanov and Barnatan found more efficient proofs. So their proofs use extensions of Khovanov homology to tangles. And initially, this map KHF was only well-defined up to an overall sign, but then various people found ways to resolve this sign ambiguity. And then quite recently, Morrison, Walker, and Wehrli showed that even Khovanov homology is in fact functorial in S3 cross I. So this is like one of the main properties of even Khovanov homology. But today, I want to talk about odd Khovanov homology. So odd Khovanov homology was discovered by Oswald Rasmussen Szabo, 2007. It's inspired by Hegardt-Fleur homology. So it should admit some spectral sequence that converges to the Hegardt-Fleur homology of the orientation reverse of the branch double cover. It agrees with even Khovanov homology over Z2 coefficients, but not over integer or rational coefficients. And then around 2008, Chris Putera defined this generalized Khovanov bracket. And in the version that I want to consider in this talk, this Khovanov bracket depends on a parameter pi. And if we set, pi equals 1, we get the Barnatan's even Khovanov bracket. And then if we set pi equals -1, we get an odd Khovanov bracket, which recovers odd Khovanov homology. And similar work was also done by Belyakova-Wagner. And then quite recently, Nice Putera and Dean Spiropoulos extended out and generalized Khovanov homology to tangles. But so until last year, or maybe year before, so it remained unknown whether odd Khovanov homology is functorial. And so this is what we can prove. So more generally, we prove that the generalized Khovanov bracket is functorial in R3 cross I. So more precisely, what this means is that every smooth link cobordism in R3 cross I induces some map on the generalized Khovanov bracket, and this map is well-defined up to homotopy and invertible scalars. And so I should say that our proof of this theorem is non-local in the sense that it does not use tangle invariant, but it's at least partially conceptual, so it's not just a brute force calculation. And so we work over this ring in one variable pi that squares to 1. So Putera used a slightly larger ring. This theorem should also hold over this larger ring, but we didn't prove that. And then if we set pi equals -1, we get that odd Khovanov homology is indeed functorial up to sign. And as you know from Wednesday, so very recently, Dean Spiropoulos found a new proof of this corollary. So his proof uses the nice Putera tangle invariant. So here's the plan of the talk. So first, I want to recall the definition of the generalized Khovanov bracket. So I will give quite some details. Then I want to outline the proof of functoriality, and I also want to discuss some properties of the odd cobordism maps. And then in the second part of the talk, I want to discuss a new module structure on odd Khovanov homology, and then I want to explain how it's related to the odd cobordism maps, and then I'll do a calculation to show why this module structure is useful. So I'll start with the definition of the generalized Khovanov bracket. So to define it, one has to choose an arrow at each crossing. This arrow has to connect the two branches of the zero resolution. So in this picture here, it would like either point to the right or to the left. And the generalized Khovanov bracket is then some chain complex in Putira's category. So Putira's category is some generalization of Barnaton's category. So the objects are just resolutions in the plane, so just circles in the plane. And the morphisms are formal linear combinations of so-called chronological cobordisms, and these are subject to some relations. So let me say a bit more about this. So a chronological cobordism is some surface, two-dimensional cobordism embedded in R2 cross I. And so what we want is that the projection onto the second factor restricts to a separating Morse function. And we want that index 1 and 2 critical points are equipped with orientations of their descending manifold. So this means that like if you have such a cup or a birth, it has no orientation. But if you have a death, it can be either oriented clockwise or counterclockwise. And likewise, saddles come with orientations. I will depict these as arrows. Sometimes I will omit these arrows, and in such cases, it will be assumed that deaths are oriented clockwise and saddles are oriented to the right or to the front, just whichever makes sense. And then, so here are some of the relations that Putira imposes on such cobordisms. So if we reverse the orientation of a death, we get a factor of pi. Same if we reverse the orientation of a split, but if we reverse the orientation of a merge, then this cobordism remains unchanged. Also, if we if we have two distant split cobordisms, they pi commute in the sense that if we reorder them vertically, we get a factor of pi, whereas if we reorder two merge cobordisms, we get no such factors. And then there are also these Barnaton relations, and then there's this additional relation. So this relation follows from the others. And what it basically says is that if you have a higher genus chronological cobordism in Putira's category, then it is invariant under multiplication by pi. And it can be deduced from the other relations and some isotopies. And there's also a grading that will play a small role in this talk. So Putira defines this chronological grading of a cobordism, the Z cross Z grading. For this talk, only two specializations are important. So there's the quantum grading, the supergrading. The supergrading is the modulo 2 reduction of the second component of this chronological grading. So what this really means is that basically deaths and splits have odd superdegree, and merges and births have even superdegree. And the supergrading has to do with the commutativity behavior of the cobordism. So if I have like two distant odd cobordisms, then they pi commute in the sense that if we reorder them, we get a factor of pi. And if S1 or S2 is even, then we get no such factor. So this is Putira's category. And now we can return to the definition of the generalized Khovanov bracket. So start with some link diagram. You choose these arrows at the crossings, and then you can, of course, replace each crossing by one of its resolutions. So you can form a resolution cube as usual. And then you can assign a saddle cobordism to each edge. But now, because we have these arrows at the crossings, we can orient these saddle cobordisms, so we can think of them as actual chronological cobordisms or as morphisms in Putira's category. So if we do this for this diagram of the trefoil, we get this resolution cube. So for example, this arrow here corresponds to this chronological saddle cobordism. And of course, if you have any two-dimensional face in this cube, it corresponds to a pair of saddles. And so the relations in Putira's category imply that each face either commutes or pi commutes. And of course, we want to get a chain complex. So we want squares to anti-commute. So how can we do this? Well, in this example, it's easy. If you stare at this picture very carefully, you see that in this cube, there are only two faces that pi commute, namely the faces that meet along this edge here. So what we can do is we can multiply this edge by pi, then we get the commuting cube, and once you have a commuting cube, it's easy to make it anti-commute. But in general, it's a bit more difficult, because it can also happen that faces both commute and pi commute at the same time. And this happens for faces of the hypercube that correspond to one of these two configurations. So here, the circle is the input of the configuration, and the arrows are the saddles. And the problem with these configurations is that they correspond to cobordisms that are invariant under multiplication by pi. So you can't tell whether they commute or pi commute. They kind of do both, these saddles. And therefore, one has to make a choice. And there are sort of two reasonable choices that lead to chain complexes. So they're called type X and type Y. And in type X, it's assumed that this configuration on the left, pi commutes, and the one on the right commutes. And then in type Y, it's the other way around. And so one chooses one of these two types, and then one can define a commutativity cochain, just like a two cochain, which records whether each phase commutes or pi commutes. So it sends a phase to 1 if it commutes, and to pi if it pi commutes. And then to make the resolution cube anti-commute, one just rescales each edge map by some sign or by an invertible scalar. And what one wants is that these scalars form some cellular one cochain whose coboundary is minus the commutativity two cochain. So such a choice of signs or invertible scalars is called a sign assignment. So this is part of it's a choice that one has to make. And if we do this for this diagram, we get this picture. So you can see that there are some signs here, and I guess here and here, and here there's also a factor of negative pi. And now this cube anti-commutes, so we can flatten it to a chain complex by just taking formal sums of terms that are on top of each other. And this chain complex is a generalized Khovanov bracket. And Putra proved that the homotopy type of this complex is invariant under Reidemeister moves. So he defined explicit chain maps for each Reidemeister move. One can also ask, how does it depend on the arrows at the crossings and the chosen sign assignment? And the answer is, well, as long as one stays within one of the two types, like type X or type Y, it almost does not depend on these choices. I mean, any two choices give isomorphic complexes, and the isomorphisms are almost canonical. There's also the issue of gradings. So this is kind of technical, but there's a reason why I'm mentioning it. So in the resolution cube, one can formally shift the quantum degree and the super degree in such a way that all differentials become grading preserving. And for the super degree, the shift at the vertex alpha is given by the modulo 2 reduction of this quantity here. Now, sort of the precise formula is not important. What is maybe important is that this right-hand side is always an integer. So the modulo 2 reduction makes sense, and the modulo 2 reduction stays the same along merge edges of the cube, but it changes along split edges. So the reason why I'm mentioning this is because this quantity S, the alpha, will show up later in my talk. And so finally, how do we get the odd Khovanov complex from the generalized Khovanov bracket? Well, we first just set pi equals -1. So this turns Putra's category in some kind of an odd Putra category. And then we apply some odd TQFT functor. This functor is completely explicit. It was already defined by Oswald, Rasmus, and Szabo. And if you have some resolution, then the associated TQFT module is just an exterior algebra in variables, and the variables correspond to the connected components of the resolution, so to the circles in the resolution. There's also such a reduced submodule, which is kind of the subalgebra of the exterior algebra that's generated by differences, and this submodule gives rise to reduced odd Khovanov homology. And finally, I should say that later we'll also consider chronological cobordisms with dots, and in some sense, the dots correspond to the variables. So this is all I wanted to say about the definition of the generalized Khovanov bracket. So any questions about this? So then I'll come to the proof of functoriality. So of course, what we do is if we have a link cobordism, we represent it by a movie of link diagrams, so that consecutive diagrams differ by elementary moves, like Reidemeister moves, more modifications isotopes. And then we have Carter-Saito's theorem, which says that two movies represent isotopic link cobordisms if and only if they differ by certain movie moves. So for example, this is what I've shown here is movie move 13, so the move consists in exchanging the movie on the left by the movie on the right. And so to prove functoriality, we have to do the following thing. So first we have to assign a chain map between, to each elementary link cobordism that connects two consecutive diagrams in a movie. Then if you have a longer movie, we can just assign a chain map by composing elementary chain maps. And then we have to prove that these chain maps are invariant under the movie moves. And the first step was essentially done by Putera. So he sort of explained how to assign chain maps to elementary link cobordisms. So this is sort of straightforward. So if you have a link cobordism that corresponds to a single Reidemeister move, you just assign the Reidemeister chain map. If you have a link cobordism that's a birth, you assign a cubical chain map that's given by a birth at each vertex. For a death, it's almost the same. So you assign a cubical chain map that's given by a clockwise death at each vertex, but then you have to rescale by some factor of pi, because otherwise it wouldn't be a chain map. So that's where this quantity SD alpha from before shows up again. And then for a saddle cobordism, it's a bit more complicated. So if a saddle cobordism, you consider a larger link diagram, D, with one extra crossing. And so the extra crossing is in the place of the saddle, so that if you resolve it in the two ways, you get like the diagrams DI and DI plus 1. And then you can look at its generalized Khovanov bracket, and you can realize it as such a mapping cone. And now the saddle chain map, so the map that we assign to a saddle is defined to be the map that appears in this cone. So that's how you assign chain maps to elementary link cobordisms. But now we have to prove invariance in the movie moves. Of course, I'm not going to discuss all of the movie moves. I only want to discuss two movie moves, so I'll start with movie move 10. So this is what it looks like. And if you look at the right-hand side, the movie on the right it's actually not very interesting. All frames are the same. So the movie on the right is just a trivial movie of the identity cobordism. So it just induces the identity map. The movie on the left, so this movie is a bit more interesting. So any two consecutive frames differ by a Reidemeister move, and then the initial frame is the same as the final frame. So to prove invariance under this move, we have to show that the movie on the left also induces the identity map, at least up to sign and homotopy. So how do we do this? Well, so I'll quickly outline the argument. So I want to consider what I call a simple tangle diagram. This is sort of unofficial terminology. I just use it for this talk. So it's a tangle diagram S that looks like this. It has an inner part C, which is just a crossingless matching with no closed component. And then it's surrounded by an affine braid in an annulus. So an affine braid is just like a bunch of strands that go from the inner component to the outer component of the annulus. Boundary component. The strands are allowed to cross each other, but they're not allowed to turn back. And you should notice that every diagram that appears in movie move 10 is of this type. In fact, the diagrams in movie move 10 are all braid diagrams, and braid diagrams are special cases of these simple diagrams. And so what Bernotan observed in the even setting is that if you take the even Khovanov bracket of such a diagram, it has no interesting automorphisms. So what this means is every automorphism in the homotopy category is just either homotopic to the identity or minus the identity. There are just no other automorphisms. And this immediately, so in the even setting, this immediately implies invariance in the movie move 10, because it just says that this chain map that appears in the movie move, it has to be the identity or minus the identity, because there's nothing else. But now how can we translate this to the odd setting? So as I mentioned before, we don't want to use tangle invariance. One could, but I mean, Dean showed that very recently that it's possible for at least for odd Khovanov multi, but we don't want to use tangle invariance. So what do? We start with such a diagram S, and then we close it up to a link diagram by putting any tangle T on the outside. So we look at the link diagram of the form S union T, where T is the outside tangle. And this tangle could be complicated. It could have lots of crossings. What we can show is that the generalized Khovanov bracket of S union T has no interesting automorphisms that are induced by Reidemeister moves that act on S. And the argument is a bit technical, but I kind of want to outline it because I want to convince you that we do have a proof of functoriality. So how do we prove this? So we start with this tangle diagram S union T. So S is this inner tangle, the simple tangle that has this part C, the crossingless part that's surrounded by the affine braid beta. And then we have some tangle cobordism F that acts on S, and that is given by a sequence of Reidemeister moves. So we look at this diagram S union T. On this diagram, we consider the link cobordism that's given by F on the inner part and by the identity on the outer part. And this induces some chain map phi. And to prove the lemma, we have to show that this map is uninteresting. So it's homotopic to the identity of two invertible scalars. So how do we do this? Well, what we do is we pass to a more complicated link diagram. So around this affine braid beta, we insert two more affine braids, beta inverse and beta. And then on this more complicated link diagram, we can again consider a cobordism that's given by the same F on the rep part and C beta, and by the identity cobordism on the outside. This again induces some chain map phi prime. Now, of course, you can use like inverse Reidemeister two moves to undo this beta inverse beta pair. Then you get back to the original diagram. So you have this homotopy equivalence with the original generalized Khovanov bracket. And what we can show, this is not entirely obvious, but quite obvious, what we can show is that this square commutes up to homotopy. And this means that instead of showing that phi is uninteresting, we can now show that phi prime is uninteresting. It's equivalent. But that seems like a more complicated problem, right? Because this diagram that here has probably a lot more crossings. But it's actually easier. The reason why it's easier is because we can move these parentheses here. So we can write it like this. So we can group together this beta inverse and beta. And then we have this beta inverse pair. We can undo it by using inverse Reidemeister two move. This takes us back to the original diagram. So we get the different homotopy equivalence to the original Khovanov bracket. So the one the left homotopy equivalence is given by undoing this pair, and this one is given by undoing this pair. And then we can fill in this diagram. We can define a map psi here by just composing this map with the homotopy inverse of this map. And then obviously this square commutes up to homotopy. So now we can show that psi is uninteresting. And that turns out to be easy. And why is it easy? Well, if you look at it carefully, you see that all the interesting things in psi happen to the left of this disjoint union symbol. Because psi is this composition. And here, so this map, phi prime, Phi prime was induced by this cobordism, which only acts on this red part. So it only acts to the left of the disjoint union symbol. And this map here was given by, well, creating or undoing this pair. So this also happens to the left of the disjoint union symbol. So in some sense, the interesting part of psi happens on C. So C is supported, this map is supported on C. And more concretely, what this means is that it preserves the resolutions of all crossings in beta T. But C was a crossingless tangle, so it doesn't have any crossing. So this means this map psi that you see here preserves all resolutions. So it's just a cubical chain map. So maybe you can think of it like this. If you have this were the resolution cube, then it's just given, this psi is just given by a bunch of maps acting on the vertices and so on. And we also know that it's a homotopy equivalence because like phi prime is a homotopy equivalence. And so it comes with some homotopies. But those homotopies are also cubical for the same reason. And this means because they're cubical, they must preserve the homological degree. But homotopies are not allowed to preserve the homological degree unless they're zero. So this means the homotopies are zero. But this means that this map psi is not just a homotopy equivalent, it's a chain isomorphism. And this means that each of these components of psi are isomorphisms. So now we can focus on one of those components. For example, we can look at some resolution d alpha, and we can look at the component of psi that acts on this resolution. And this is a morphism in Functorial's category, so it's some linear combination of chronological cobordisms. Let's assume for simplicity it's just one chronological cobordism. And then this cobordism has a part that lies on C over C, and a part that sort of lies over beta T or over resolution of beta T. But again, psi is uninteresting in beta t. So this map, whatever it is, or this cobordism can't have any interesting topology over beta t. So if it's non-zero, it can only be an identity cobordism over beta t. Over the other part, over C, it could have interesting topology, but it has to be an isomorphism. This means it also means it must have quantum degree 0, and because it sees a crossingless tangle with no closed components, there are no options. The only option is that it's also the identity. So it has to be some scalar multiple of the identity, where this has to be some invertible scalar. So now we see that at each vertex, we see such a scalar multiple of the identity. And in principle, these scalars could vary from vertex to vertex, but we also know that psi is a chain map, and this implies that all scalars must be the same. And so it follows that psi is itself just an invertible multiple of the identity map. And so, because everything commutes, we see that our original map phi is homotopic to an invertible multiple of the identity map, and that proves the lemma. So this takes care of moving move 10. It also takes care of moving moves 1 through 9. Well, the first few moves are obvious anyway, but it also takes care of those moves. Let me see how much time I have. So then for some other moves, we do have to make some explicit calculations. I don't want to say too much about that, but the trick is that in all those moves where we do have to compute something, we can choose the signs carefully. So the problem with odd Khovanov multi is always that it's difficult to work with the signs, but it turns out that in every single case, we can just choose, where we have to do computations, we can choose signs explicitly, and then we can just compute the two signs of the chain maps assigned to the two sides of the move, and we just see that the chain maps agree up to invertible scalars. So this is kind of a summary of our proof of functoriality. So any questions about it? So next I want to discuss some properties of the odd cobordism map. So far I talked about generalized Khovanov multi, but in the remainder of the talk I will mostly talk about odd Khovanov multi. So the first thing that one can show is that if F is some closed surface, a non-empty closed surface, then it always induces the zero map on odd Khovanov multi. It's of course not true for even Khovanov multi, like a torus always induces multiplication by 2 on even Khovanov multi. However, it's not true that every closed component in a link cobordism evaluates to 0. So you can have a link cobordism that has some closed components and that induces a non-zero map in odd Khovanov multi. And then another thing worth noting is that the odd cobordism maps are not invariant on the ribbon moves. Now here's a picture of a ribbon move in case you've never seen one. So you hear this is like a broken surface diagram of a portion of a link cobordism. So everything you see is like in x, y, t space. So t is time, like the vertical direction is time. And everything sort of happens in z equals 0. But then at a place where, for example, this tube is interrupted, it's understood that the tube dips down in z direction. So here this tube undercrosses the horizontal sheet. And here it's the other way around. So here the horizontal sheet undercrosses this tube. And the ribbon move just consists in replacing, so here the tube overcrosses, right? The ribbon move just consists in replacing an overcrossing tube by an undercrossing tube. And the even cobordism maps are known to be invariant under this operation, but the odd ones are not. And maybe more surprisingly, the odd cobordism maps are also not invariant under smooth ambient isotopies in S3 cross I. And here's an example. So these are, again, broken surface diagrams. So both pictures show cobordisms from the unknot to the two-component unlink. So here we have this tube, and then we have a cup whose top boundary is given by B. And in this picture, the tube overcrosses the floor of the cup, and here the tube undercrosses the floor of the cup. And obviously, these two pictures are related by a ribbon move, but the cobordisms are also related by an ambient isotopy in S3 cross I, because what you can do is you can sort of take the floor of this cup, and in S3 you can move it around to make it go on top of the tube. But it turns out that these two cobordisms induce different maps on odd Khovanov multi. And there are actually infinitely many such examples, so there are infinitely many cobordisms that are all mutually ambient isotopic in S3 cross I, but that all induce different maps in odd Khovanov homology. So it's odd Khovanov homology is just not functorial in S3 cross I. Now you can ask, how badly does it fail to be functorial in S3 cross I? And this is now a bit speculative, a part of it. So we can consider the following setup. We can start with a link in S3, and we can pick a base point in its complement. And then we can think of this link as sitting in the complement of the base point. Of course, the complement of the base point is just a 3-ball, an open 3-ball. And Morris and Wehrli explained to us how to assign like Khovanov type homology theories for links in abstract 3-balls. So to this link, together with the base point, we can assign some concrete odd Khovanov homology group. This group is only defined up to some sign because odd Khovanov homology is, only functorial up to sign. So it's kind of a projectivization of the group, but still we can assign something. And this group depends on the chosen base point. And if you have 2 base points, then the corresponding odd Khovanov homology groups are isomorphic. But the isomorphism depends on a path between the 2 base points. And the path has to be in the link complement. And now we believe that the following is true. So we believe that so if you have 2 base points, then the path between the base points doesn't actually matter. All that matters is a lift of the path in the branch double cover. And how would you prove this? Well, so to prove something like that, you have to see so you look at the path between 2 base points, and you have to look at what happens when this path winds twice around the meridian of the link, because in the branch double cover, this would kind of be the same as not going about the meridian. What this means is you have to study the sweep around map, so the map that is induced by taking one strand of your link diagram and moving it around the rest of the link. And in the even setting, Morris and Wehrli proved that the sweep around map is the identity map. In the odd setting, it's not the identity map, but we think we can compute it explicitly. That's a bit preliminary, and we are pretty sure that it squares to the identity. Computing the square is easier than computing the map itself. So this would show this claim. And then if you have, this is again a bit speculative, if you have a path that lifts to a loop, then you should get a monodromy action on odd Khovanov homology. So this would be an action maybe up to sign. It would be an action by the fundamental group of the branch double cover. So it should act on odd Khovanov homology up to sign. I don't know to what extent this action would be non-trivial. And then there's also some maybe conjecture about how odd Khovanov homology would be functorial. So maybe the assumption is it should be functorial in S3 cross I if one also picks some path in the complement of the link cobordism. So this is still a bit speculative, but I want to mention one more property of the odd cobordism maps. So remember there's these 2 types of odd Khovanov homology, type X and type Y. And it is known that these 2 types give isomorphic homologies. And this result has a bit of a history. So the original proof was somewhat incomplete. Then Chris Putera claimed to give a correct proof, but I don't understand it. I was also unable to reach Chris. And just yesterday, I discussed it with Leo Shellstraat, and he was also not entirely sure whether it's correct. But Bayer and Sarkas, Daduto, Stoffregen gave correct proofs. So it's really true that type X and type Y odd Khovanov homology are isomorphic. But you can also ask, what about the cobordism map? Do the 2 types give rise to the same cobordism maps? And the answer is yes. So there is a homotopy equivalence between the type X and type Y, or generalized Khovanov brackets actually, and this homotopy equivalence intertwines with the cobordism maps. And I should say something, so this is an interesting homotopy equivalence because it has to do, so what you do is you first flip over the link to get a new diagram, and then you kind of reflect each resolution in the plane. So it has some geometric interpretation. And in fact, this homotopy equivalence that you see here is very similar to the map kappa that appeared in Hongjian Yang's talk about involutive Khovanov homology earlier this week. And if you set pi equal to 1 and switch to the 2 coefficients, then I think his result implies that this homotopy equivalence is homotopic to the identity. But in odd Khovanov homology, it relates type X and type Y. So this is what I want you to say about the properties of the cobordism map. So any questions? So then I come to the second part of the talk. So this is about this structure on odd Khovanov homology. So this is now specifically for odd Khovanov homology. So we can show that the reduced odd Khovanov homology of a link is naturally a module over the exterior algebra of the first homology of the link's branch double cover. And where does this module structure come from? Well, it's defined combinatorially in terms of dot maps. This also means that for odd Khovanov thin links, it's not interesting because there the dot maps have nowhere to go. And it turns out to be related to cobordism maps. So I will explain that later. But first I want to give the definition of this action. So I first want to say something about dots. So we want to start with Putera's category from before, but we want to enrich it a bit by allowing chronological cobordisms to be decorated by dots. And of course, these dots have to occur at different heights. They're not allowed to occur at the same height as a saddle or a birth or a death. And it's understood that they have odd superdegrees, so they kind of pi commute with each other and with odd things. And then one also imposes these two extra relations. So this category was already described by Putera. Now, what are the dots good for? Well, we can use them to define dot chain maps. So if we have any edge E in a link diagram, we can assign a chain map of the generalized Khovanov bracket. I call this X sub E. And I also just depict it by such a picture, like the edge E with a dot on it. And how is it defined? Well, it's just a cubical chain map. On each vertex, it's just given by a dotted identity cobordism, where the dot sits above the edge E, and then one again has to rescale by some factor to make sure that it's a chain map. And so the dots on edges kind of act on the generalized Khovanov bracket. And from now on, I will always assume that pi is equal to -1, so it means we'll have an odd Putera category, and it also means that this factor here is just a sign. And then we can ask, well, what happens if we move these dots across crossings? And we have this lemma. So in type Y, the homotopy type of the dot chain map does not change if we move the dot over a crossing. And this result was essentially shown by Mannion. So Andy Mannion worked in a different setting. He wanted to define some totally twisty dot Khovanov homology. So for him, the dots were part of the differential. But basically, his proof just translates to our setting. So it follows that these two dot chain maps are homotopic, and the homotopy between them is explicit. So in type Y, we can slide a dot over a crossing. Now you can ask, can the dot also go under the crossing? Like, can the dot go from here to here? And in other words, can we find some homotopy that would allow us to sort of move the dot under the crossing? And one could try to change this homotopy just a little bit by reversing the orientation of the saddle. And this almost does the right thing. So if you only look at the crossing C, that does the right thing. But sort of this new homotopy that you get doesn't interact nicely with components of the differential that come from other crossings. So that doesn't quite work. But nevertheless, there was sort of, I guess, some people assumed that dots can overcross and undercross. But that's not true. Can show that it's false. So it turns out that in type Y, dots can only overcross, and in type X, they can only undercross. And in the entire rest of the talk, I will work with type Y because that's basically what Putera does. He never says it very explicitly, but he implicitly works with type Y. So from now on, dots can overcross, but they can't undercross. And then you can ask, well, what would happen if a dot just tried to undercross? And here's what happens. So let's look at the crossing. Let's label the incident edges A, B, C, D, and let's consider the corresponding dot maps XA, XB, XE, XD. And it's easy to see that these maps satisfy this relation, XA plus XE is XB plus XD. And this relation is not up to homotopy. It's just literally true because it's true in each resolution. But now, because B and D are related by an overstrand, we know that these two maps on the right-hand side are homotopic. So this is homotopic to 2XB. So we see that XC is homotopic to 2XB minus XA. But this is now precisely the relation that holds in the coloring module of the link diagram. So what's the coloring module? It's just the free abelian group formally generated by all overstrands, and so kind of all arcs and all overstrands in the diagram. And for each crossing, you get such a relation. So here, the generator C is equal to the generator 2 times generator B minus generator A. And so the point is now, because this relation is the same, exactly the same as the relation satisfied by the dot chain maps, we see that elements of the coloring module act on type Y odd Khovanov homology by dot maps, or linear combination of dot maps. Now there's also a reduced coloring module. This is just the kernel of the obvious homomorphism that sends each generator to 1, or equivalently, the reduced coloring module is just generated by differences of generators. But now remember that in the odd setting, the way reduced odd Khovanov homology can be defined is you just take differences of variables. So differences of dot maps act on reduced odd Khovanov homology. And this means that elements of the reduced coloring module act on the reduced type Y odd Khovanov homology. But now dots are odd, so they kind of anti-commute, and this means that we get an interaction of the entire exterior algebra of the coloring module. And now, it's well known that the reduced coloring module is just the first homology of the branch double cover. And this is correspondences, maybe I'll skip it, but it's almost not the theorem. It almost just follows from the definition, because you can, to see this, you can start with the vertical presentation for the knot group, and this gives you a handle decomposition of the knot complement with like a 0 handle for the base point, and then you can easily construct the handle decomposition for the branch double cover, and then you just compute the first homology, and you see that it's the coloring module. So it is very explicit. So we get this action of the exterior algebra of the first homology of the branch double cover on the reduced odd Khovanov homology. And now I want to do some examples where we can say more about this action. So first I want to consider the case where L is a knot. Of course, in this case, the branch double cover is a rational homology sphere. So its first homology is torsion, and this means that if you work with rational odd Khovanov homology, the action has to be trivial. In particular, because the action is given by dot maps, this means on the rational odd Khovanov homology of a knot, difference of dot maps must act by 0, just because they act by torsion. So this means that in the rational odd Khovanov homology of a knot, any two dot maps are the same. So for the rational odd Khovanov homology of a knot, it's actually true that dots can move freely along the knot. They can overcross and undercross. But these assumptions here are essential. So this is, if it's not a knot, then this is not true. For example, here we have two pictures. And you see, so this picture and this configuration. And you see in both of these pictures, the two dots are on this component. But it turns out that this picture acts by 0 on rational odd Khovanov homology, and this picture acts by a non-zero map. So the dots cannot move freely along a component. So this assumption that in this corollary, this assumption that we have a knot is essential. Now we can ask, what about this component assumption? So let's say we have a knot, and we look at the integer odd Khovanov homology. Can the dot move freely along the knot, or is there an example of a knot where the location of the dot actually matters? And well, any such knot would need to have some interesting torsion in its odd Khovanov homology, because kind of the first homology of the branch double cover is torsion. And luckily, Alexander Shumakovich has done a lot of nice computations. So he found knots with interesting torsion in odd Khovanov homology. So here you see the reduced Khovanov homology of the 3,3 minus 3 pretzel knot. So it's from Shumakovich's paper. So the numbers are the ranks of the chain group. On the left, you see the even reduced Khovanov homology. On the right, you can see the odd reduced Khovanov homology. And you see that the only difference is that in the odd theory, you have this piece of Z mod 3 torsion. And Shumakovich kind of said there must be some symmetry that explains why this torsion is there. And I can't sort of explain why it has to be there, but I can tell you how it's related to the dot chain maps. So let's see. So this is the 3,3 minus 3 pretzel knot. Now consider this small loop C. It obviously has even linking number, I guess linking number 0, so it lifts to a closed curve in the branch double cover. We can ask, how does this curve act on odd Khovanov multi, and it turns out that it acts by a non-zero map. And maybe if I go to the previous slide, it acts by a non-zero map from this Z2 summand to this Z mod 3 summand. So this shows that for a knot, this action can be non-trivial. And how do we actually, and this also, so this action of this curve just corresponds to an action of the difference of dot maps. So this means that this difference of dot maps acts by something non-zero. And maybe how do we compute this action? How do we prove that it's non-zero? Well, we don't compute it directly. We look at some larger link diagram where we plumb in some extra twisted band. And then we can identify the co-kernel of this difference of dot maps with some odd Khovanov multigroup of this diagram, and we can just plug this link into knot job, and we see that this group is 0, so this co-kernel of this difference of dot maps is 0, so the difference of dot maps is surjective. Okay, so this shows that the module structure can be interesting even for a knot. But now we can ask, is it good for something? Is it related to cobordism maps, for example? And the answer is yes, so there's a concrete relation. So consider some arc alpha that's in the complement of, or let's say that meets the link only in the endpoint. So here in this picture, this is this blue arc, and these vertical black strands are sort of parts of the link. And then we can look at the preimage of this arc in the branch double cover. So the preimage, of course, consists of two arcs which meet at the endpoint, so it's a closed curve. And then we can choose some orientation convention, so then we can form some closed curve in the branch double cover. So it presents some homology class. We can then ask, how does this homology class act on odd Khovanov multi? And how is it related to, is this action related to cobordism maps? And we can answer this question explicitly. So firstly, we have an explicit formula for the action of this homology class in terms of dot chain maps. Maybe I don't want to go into detail, but say a bit more. And secondly, so we can now look at the link cobordism that looks like this. So this is, again, a broken surface diagram. The vertical direction is time. So we basically have these sheets, which just form an identity cobordism. And then we have this horizontal tube that connects them, and that sort of overcrosses and undercrosses in the intermediate sheet in the same way as this arc overcrosses and undercrosses other strands. And this picture induces some odd cobordism map, which is well defined up to sign. And it turns out that this odd cobordism map is precisely the action of this homology class. So actually, up to sign, we could express this action in terms of cobordism maps. And this also shows that if you have a tube that overcrosses all intermediate sheets, then the action is very simple. It's just a difference of dot maps. This follows from the first formula. But if it undercrosses strands, the action becomes more complicated. And this again shows that the odd cobordism maps are not invariant under ribbon moves. And this is in type Y. In type X, it would kind of be the other way around. So in type X, the undercrossing tubes induce simple maps. And then, so let's see. There's another slightly different connection with cobordism maps. So if you have a link cobordism that's presented as a movie, we can define the coloring module of the link cobordism. And there's sort of two definitions. The first definition is we just take the direct sum of all the coloring modules of the link diagrams that appear in the movie, and then we impose some obvious relations. Basically, in two consecutive coloring modules, we just identify corresponding generators. Then there's this other definition. So if F is given by a broken surface diagram, we can look at some free abelian group generated by the oversheet modulo some relations. So then we get the coloring module of the link cobordism. This can again be related to the homology of the branch double cover. And now, if you have a link cobordism, we can decorate it by an element of the exterior algebra of the coloring module, and then to such a decorated link cobordism, we can also assign some cobordism map. Now, I don't want to discuss this in general, but I just want to look at a special case. Namely, I want to consider the case where we have a 2-knot, and then we put the single dot on some oversheet A. So we get some dotted 2-knot. This dotted 2-knot induces a map on the odd Khovanov multi. This map can now be non-zero because the 2-knot contains a dot. If it didn't contain a dot, it would be 0. But this dotted 2-knot induces a map on an odd Khovanov multi. This map is just given by some multiplication by some scalar. And you could say, well, maybe the map could depend on the location of the dot, but it actually doesn't. It's just an invariant of the 2-knot. and it's in some sense some kind of an odd Khovanov-Jacobson number. And by the way, it's easy to see that it's always odd because from the comparison with the two Khovanov homology, because in the even setting, it's always equal to 1. So we have this odd Khovanov-Jacobson number for dotted 2 knots. And now what's the interpretation? Well, we can prove this theorem. So if F is either a ribbon 2 knot or an even twist spun knot, then this odd Khovanov-Jacobson number is just equal to the determinant of the 2 knots, so the order of the first homology of the branch double cover. And this should be true in general, and it's probably there are proofs by using some known spectral sequences to Floer theories, but there are probably some technical details that will need to be worked out. But we can prove it combinatorially for ribbon 2 knots and even twist spun knots. And I think in the remaining minutes, I want to show you how to prove this for ribbon 2 knots, because this is kind of a nice application of this module structure that I discussed. So here we have a ribbon 2 knot. Again, it's a broken surface diagram. Vertical direction is time. So we have some unknotted spheres that are kind of connected by tubes. And in this setting, we have such a ribbon 2 knot. So the rule is that the tubes are not allowed to kind of pierce through each other, but they're allowed to kind of pierce through the spheres in this broken surface diagram. And then we can always assume, by assuming maybe some handles kind of sliding tubes over others, we can assume that all tubes connect to this sphere as 0. This is the case in this picture. So we have like this tube from S1 to S0, and then a kind of complicated tube that goes like this. And we can make further assumptions. We can also assume that sort of if you go forward in time, then the births at the bottom of the two spheres occur first, the tubes occur next, and the deaths occur last. This is not what you see in this picture. Like here, this tube comes first, but we could push it up a bit. So we can assume that we first have the births, then the tubes, then the deaths, and we can assume that the tubes occur one after the other. And then we can puncture the 2 knot at the north pole and the south pole of S0, and then we get some concordance from the unknot to the unknot. And I now want to look at the induced map actually on a reduced odd Khovanov homology. So that basically this map will give us the odd Khovanov-Jacobson number. So I want to compute this map actually. How do we do this? So because the cobordism is a composition of birth, tubes, and death, this map is just a composition of such maps. Birth maps followed by tube maps, followed by death maps. And I first want to compute the tube maps. And for this, I want to look at the unlink that occurs right after the birth. So these circles that you see here are kind of the small circles that, if I go to the previous slide, that go around the south poles of these spheres. And then I also have these blue arcs. These represent the tubes in the ribbon 2 knot. And then I also want to consider these trivial arcs epsilon, so they don't overcross or undercross anything. And then if I look at the preimages of the epsilons in the branch double cover, they form a basis for the first homology of the branch double cover of this unlink. And this means that if I now take the preimages of the alphas, I can express them in these spaces. So I can write them like this here, get some coefficients, denote by A the matrix that contains these coefficients. And now I want to compute the map induced by all of the tubes. So I consider the cobordism given by, it's like an identity cobordism with some tubes attached to it. And because of what we saw before, we know that the odd cobordism map that is induced by these tubes is the same as the action of this wedge product of homology classes. And because of this formula, this wedge product is just determinant of A times with this wedge product. But these epsilons were these trivial arcs, and because they're trivial, they just act by simple differences of dot maps. Now we can expand this product, and then we get a single term here that doesn't contain x0. So x0 would, like, before we had this sphere as 0, and x0 kind of corresponds to a dot there. So we get this leading term and some other terms. So this is an explicit formula for the map induced by the tubes. Now to get the entire cobordism map, we have to precompose with the birth maps and the death maps. And what this does, it kills all these other terms, and it evaluates this term to plus minus 1. So we see that the cobordism map is just maybe up to sign, it's just determinant times the identity. And this means that this odd Khovanov-Jacobson number is just the determinant of A. And so it remains to identify the determinant of A with the first homology of the branch double cover of the ribbon 2 knot. And this is easy because you can just write the ribbon 2, so obtain the ribbon 2 knots by gluing 2 copies of the same ribbon disk, and then So if you look at the branch double cover of the ribbon 2 knot, it has the same first homology of the branch double cover of this ribbon disk, and then you can find some handle decomposition of this branch double cover, and this will show that this matrix A from before is just a presentation matrix for the first homology of the branch double cover. So this proves this theorem for ribbon 2 knots, and actually I can even mention the theorem for even proof for even twist spun knots. So we still want to show that for an even twist spun knot, this odd Khovanov-Jacobson number is the same as the order of the first homology of the branch double cover. And for this, we use some completely different idea. So if you look at this slide, it's not clear why it's related to even twist spun knots. So we start with some framed knot K. This knot has nothing to do with the knot that we're going to use for building the twist spun knot. Just some framed knot in R3. What we want to look at is we want to look at the end cable of this framed knot. So just the ordinary end cable and just end parallel strands. And now I want to make an assumption. So I assume that either the framing of K is even or N is even or both. And in this case, we can show that the odd Khovanov homology of the end cable carries an action of some Hecke algebra at square root of -1. And this action is defined in terms of cobordism map, but it's well defined, so we can fix the signs. It's really there. And this theorem was the starting point for our own project. So we wanted to prove this theorem, and that's why we proved functoriality of odd Khovanov homology. But initially, we thought that it would hold without any assumptions, but this assumption here on the framing or on N is actually necessary. So we believe that if K has odd framing and the number of strands is odd, then we don't have a Hecke algebra action. Instead, we should have a symmetric group action, which is similar to the action in the even setting. And in some cases, we can give a stronger version. We don't just have a Hecke algebra action, but an action of some temporal Lieb algebra where the circle evaluates to 0. So that's some quotient of this Hecke algebra. And I don't know whether I have time. Maybe I have to. I didn't plan to explain how this is related to ribbon 2 knots. But how can we use this stuff to show that the odd Khovanov-Jacobson number of a ribbon 2 knot is the first homology of the branch double cover? So, okay, so what we do, just the usual N cable, just N parallel strands, just the usual N cable. So maybe I explain how we get this, how we can use this to prove this. So the goal is to prove that. So if not ribbon 2 knot, so if let's say F is an even twist spun knot. We'll see later what that is. It's a kind of knot. Then our result holds, so that this odd Khovanov-Jacobson number is the order of the first homology of the branch double cover. So that's what we want to show. And how do we do that? Okay, I didn't really. So we start with an unknot. So this will be our knot K. Our knot K is now just an unknot. And then we consider some 1-1 tangle T, and I have to explain in a second what this picture means. So here, the vertical direction is actually time. And so this tangle kind of goes in time direction. So more precisely, we want to look at some normal disk to this, let's call it D, to this unknot. And then this tangle just lives in D cross I, where I is the fourth coordinate. Now what we can do is we can move this tangle around the unknot, and then it sweeps out some cobordism, some concordance. And actually we want to be do a bit more. So we'll assume now that this knot here is framed. And what this means is that now, as we sweep around this knot, this tangle, this disk rotates m times. So this concordance that we get depends on the framing. So we get some concordance, but at the bottom we just have an unknot, and at the top we have an unknot, so we can just cap it off. Okay. And then we get some 2 knot, so the whole thing is going to be some 2 knot. And this is precisely what is known as the M-twist spin of the tangle closure. So this is how we think of this twist spun 2 knot. So it's kind of 2 knot. And now how do we prove this here? Well, the point is now, so what we really have, this is still somewhat work in progress. We didn't write it down, but we think we have it. So we can really show that under some assumptions, this Hecke algebra action is a temporal leap algebra action, and we actually have some kind of an action of a temporal leap category. So as far as the cobordism maps are concerned, and this uses that the framing is that K is even. Oh, sorry, I call it M. This uses that M is even. Otherwise, we don't have this result. So this means that in some sense, we can think of T as being some morphism in some temporal leap category where the circle evaluates to 0. So it's a morphism from the object 1 to 1. And this means to compute this cobordism map, we can just simplify this morphism in this temporal leap category by using Kaufman bracket scaling relations. And what this shows is that this odd Khovanov-Jacobson number of this 2 naught is literally just the determinant of the tangle closure. But now, if you take an even twist spun knot, so this again uses that we consider an even twist spun knot, then the determinant of the knot that you start with is the same as the determinant of the twist spun knot. So this is the same as this here. So this is because M is even, where here by the determinant I just mean the order of the first homology of the branch double cover. So this gives us what we want. So this odd Khovanov-Jacobson number is the order of the first homology. So that's all. So thank you. Oh, that it's just like in one diagonal. Because the dot maps have degree -2, right? The octane degree. So the, yeah, right. Does that impact the stuff with the 2 knots? Yeah, it's just it's just where this whole connection with the first homology kind of comes from. I mean, it's also why maybe this is not directly related to 2 knots, but it's also why it's not invariant under these ribbon moves. But sort of morally speaking, I think if they could overcross and undercross, probably these 2 knot invariants would be trivial, I guess. I mean, I can't formally prove that. But this is something that really confused us. So when we first did the computations, we kind of assumed that the dots can overcross and undercross because other people assumed that too, and we just ran into contradictions, and it was, yeah. Right. Yes. So you can think of that I think you mean to some right. I think it's something like take the path from some point to the knot or the link. I think it should be something like that. Yeah, it should be something. Yeah, I think. Yeah, I do think they're somehow monoidal, but so of course if you have like a cobordism and then sort of a disjoint union with a closed component, you get 0. But if you have a closed cobordism that's somehow linked with the cobordism, then you get something non-zero. Well, it's just so it's just an odd version of Khovanov's TK of D. So it could also be so this was already described in the paper of Hartwig, Rasmussen and Sauber. So the way they defined the TK of T module, let me see, is so if R is some resolution with components with components A1 through AK, so these are the connected circles in the resolutions, then sort of the odd TK of T module, the way they define it, it's just the exterior algebra of these guys. You could also define it as just V tensor K, where V is the Barnard-Tans, V plus this here, but then the odd cobordism maps are just slightly different. So the odd split map is different from the odd, the even split map, if you see it in that picture. But in the odd setting, there's sort of, so the way Oswald, Rasmussen, and Sabo define the merge and split maps, it's kind of intrinsic. So the merge map is given by two components merge. The merge map is given just by identifying the corresponding variables. And if the component splits in two, it's slightly more complicated. And actually, that definition could be generalized. You could do, even for the generalized theory, instead of using an exterior algebra, you could use some pi exterior algebra, like some non-commutative algebra and some variables where the variables kind of pi commute and square to zero. So that would work. But yeah. I think so. I don't know. Maybe it could factor through the first homology of I don't know. Maybe only up to sign. And I don't know to what extent this action can be non-trivial. So in principle, you could imagine that any loop that lifts to a loop in the double cover, so any loop that has even linking number with the link, which would sort of induce the trivial monodromy, so then you would not have an interesting action, but I don't think it's the case. So I think there's some interesting action of the fundamental group of the branch double cover odd Khovanov. And I think to write it down, you need to understand these sweep around maps, and I think we have sort of a guess of what they are on chain level. And then you have to, if you have a path in the link complement, then you have to sort of compute the associated map. You maybe compose it into Wertinger generators, and then up to conjugation, each Wertinger generation corresponds to some sweep around map or something. I don't know.